I'll stand up. So
Sure.
that's
Yeah. Hello, everyone. Welcome to today's ML Idea Seminar. Today, it's our honor to invite our own speaker, Jifan, and he is a PhD student at University of Wisconsin-Madison, working with Professor Prof. Nowak. His work focuses on label-efficient learning and its modern application to large-scale deep learning systems. He is also generally interested in human-in-the-loop learning and cross-disciplinary research that apply those methods in the real world. Okay. Yeah,
right.
Jifan.
Yeah, thank you, Yuchen, and thank you for having me here to give this talk. So this has been a recent work with a lot of collaborators, as you can see on the screen. They are awesome, and I'm just here representing them to deliver what our findings here. So I'll start with giving a background on what is label efficient learning, because LabelBench is all about label efficiency. Well, in the real world, you usually start with a bunch of unlabeled data, and also you are usually annotating under a very strict budget. That means you can't really annotate all the data that's available. You have to be selective in what to annotate, what not to annotate. And so in general, the idea for label efficient learning is, well, instead of randomly choosing these points to get labeled and then train a classifier on top of it, is there a more strategic way of basically obtaining models with higher accuracy with lower labeling costs, meaning lower labeling budget? Yeah, so basically there are two objectives. Either you fix the budget, you want to have a higher accuracy for your classifier, or you fix the accuracy, so you want to achieve a certain accuracy classifier and you want to minimize your labeling cost. These are the two trade-offs that people need to see in practice. And there are many label efficient learning methods, and a lot of them are not foreign to you guys. So first of all, one way to think about label efficient learning is, well, you could take a large pre-trained model, pre-train on some large scale pre-training data set. For example, on CLIP, it takes all these image and text pairs and use that as the data set to pre-train the model. And then you have some domain specific data that you want to label. And when you do transfer learning to adapt to this specific domain, the goal, well, so first of all, this pre-trained model is going to rearrange the data inherently for you so that they look more separated. They look the right concept, like more clustered together. The representation is clearer in the high dimensional space. And then you can then label in that space under a budget. And then you basically see higher accuracy if you have the same labeling budget. So if you use a pre-trained model versus not using a pre-trained model, obviously the prior knowledge helps you to get to the higher accuracy. And if you just want to get to the same accuracy using either the pre-trained model or without the pre-trained model, you do see using pre-trained model usually gets you there with much less annotation cost. Yeah.
So are you using the pre-trained model, the representation is coming out of it, or are you using the pre-trained model to label your?
Yeah, so here I'm saying it's implicitly reorganizing the data, so you can either using the representation out of the pre-trained model and train a linear probe on top of it, or you could fine-tune the model end on the domain specific data. So this is just the mental picture. When you apply a large pre-trained model, it's inherently implicitly reorganizing your data based on prior knowledge. Obviously, when you fine-tune end-to-end, these representation can still shift a little bit. Yeah, but you are starting from a much better spot than these randomly distributed data. in its raw form. So that's one type of label efficient learning. Another type of label efficient learning is semi-supervised learning. So semi-supervised learning, you start again with the unlabeled data, you randomly choose some data to label, and then the reason why it's called semi-supervised is because you also leverage all the unlabeled data when you train your classifier. And by doing that, I mean, yeah, I think the screen is a little bit harder to see, but these lighter nodes are pseudo labels. So you're saying, well, I'm pretty sure these lighter nodes are in one class versus another. Why don't I add those data in my training set and then train my model? So you are basically taking your human label data and extrapolate other data with some pseudo labels, and then train your classifier, and that's going to give you a better model. So semi-supervised learning obviously has been studied a lot, also with large pre-trained model. And then a third method is called active learning. This also has been studied a lot. And the idea behind active learning is, well, when we choose which data to label, both of the previous methods just say, well, why don't we choose things just randomly and take a subset of the unlabeled data set and just label them? Well, active learning asks, is there a better way to curate ask which data points to label? So, and it does it in a more adaptive way. So basically, first you randomly pick some data points to get labeled. You train a classifier based on that. Then you see, well, one type of active learning is uncertainty sampling. So basically it annotates along the decision boundary that you have recently trained. So you say, well, why don't I get more labels around there? Well, then those data helps you to get a better classifier. And then you say, oh, this is my most up-to-date classifier. Why don't I get labels around there so it narrows down where my classifier is, and it gets more labels, and then end up getting the classifier. And if you look at it, it basically annotates data. So the uncertainty sampling method basically annotates data around the ground truth decision boundary. So it sort of annotate data around where the data separates, and not so much focusing on the rest of the space. So yeah, so active learning is adaptive. It's more strategic in what to choose to label. But all these three methods have been staying pretty separate in the past, I don't know, like 20 years or something. So, and some of them really just became a field, like pre-training model just became a field like in the last 5 years. So, or 10 years. So if we look at benchmarks of these different methods, if you look at large pre-trained model, for example, take Cliff, this is a table, I don't know if you can see it very clearly, but it's a table that I look at a lot. It's basically the classic table of what architecture you used and what are on each data set, what's the accuracy on it. So note that you're varying architecture, you're also varying the pre-training method, you are varying the data set, but you're really fixing the budget, meaning you're evaluating on the entire data set of CFAR 10, entire data set of CFAR 100, but CFAR 10 could actually come from a much larger pool of unlabeled data. And so, yeah, it's fixing the budget. There's no data selection, it's just randomly curated data set beforehand. And if you want to fine tune a model based on that, so like, for example, its performance on, this is not zero shot, I think it's linear probing accuracy. So so you are training a linear classifier based on this data using the clip features. And so if you want to do any sort of transfer learning, you're just using supervised training. Yeah. So in semi-supervised learning, so this is one of the state-of-art algorithms in semi-supervised learning. And the result is similar. So you vary what the method you use to train. You vary the data set you train it on. But what's fixed are architectures. So it's not using region transformer, it's using white ResNet. It's also saying, well, my really small subset, like 40 or 250 of the CFAR10 is randomly chosen from my, treating CFAR10 as unlabeled if I were. So for semi-supervised learning, these things are fixed. For active learning, it's same. So active learning results usually look like plots. And so the x-axis is usually how many examples you have annotated. So that's your labeling budget so far. Your y-axis is the accuracy that you get so far by annotating, say, 1,000 examples or 2,000 examples. And different lines represent different active learning algorithms. And I believe random sampling here is just your regular randomly choose a bunch of data, train my model on it, what's the accuracy. So you usually see these curves as you annotate more examples, your model's accuracy gets better. And for some plots, you see that when you annotate using active learning, you actually perform better than just randomly picking examples to label. And what are the variables here? You vary what are different budgets, what's the you do the experiment across different data sets. You choose you experiment against various active learning algorithms, but also here your architecture is fixed. Your architecture is usually a multi-layer perceptron or ResNet, and you're training them from scratch. And the training algorithm is usually just supervised training on the label examples. It's not using any semi-supervised learning algorithm for training. So yeah, so you can see that all three are trying to target label efficiency, and they are evaluating just in their specific domain and not caring about each other. And so in LabelBench, what we really do is saying, well, they're all label efficient methods, and there's no reason for us to focus on applying one versus another. Actually, in practice, you should apply all three of them, and that's going to give you the best performance. So we propose this framework, which is very similar to active learning framework, but have some changes. So I will just give you the overview of the framework now. So I will start with the active learning framework. So in active learning, as we said, active learning is adaptive. It chooses a batch of examples to label based on an algorithm. It labels it based on this updated data set. It feeds into the active learning algorithm again, and it chooses some example for human to annotate. So you go through this loop. And then usually in the active learning framework, you also, based on your newly collected data, you train a neural network, and based on existing benchmark, it's usually the ResNet. And you usually just do supervised training on what you have collected so far, what you have labeled so far. This ResNet usually gets trained at every iteration. It also provides some information like uncertainty, like the model's uncertainty towards some examples or some feature embedding. So it helps the active learning algorithm to make decisions on what to label next. But it is not necessary. So the active learning algorithm can also use other heuristic that doesn't involve a neural network. It can also train additional neural network as part of the active learning algorithm. But this is just so that's why the arrow is dotted. So we look at this framework and we see that, oh, it's using supervised training, but you have both labeled and unlabeled data. So why don't we use semi-supervised training there? And you have usually ResNet. Why don't you use large pre-trained models and just fine-tune those? So basically, in the LabelBench, we changed those parts of the active learning framework. We say, well, we want to do semi-supervised learning. We want to use large pre-trained models like Cliff or Coca. We also experiment on a much wider range of data set where these are the wilds data set. So it's the FMOW and IWCAM. Both of these are sort of imbalanced and more realistic data sets. And we also experiment with a much wider range of, so every time what's the batch size for my algorithm to choose to annotate, I can annotate 100 of them at the same time or 100K. Usually in the active learning literature is usually anywhere from 100 to 1,000. So, and also the total budget, we can annotate either only 1,000 images in a particular data set, or we can annotate 100K images in a data set. So we sort of experimented with a much larger range of data set and batch size scale and labeling budget scale than traditional active learning. And obviously, these two parts are the most important. So I think I'm going to pause here, and if you guys have any questions, I think it's a good time to ask, because next I will just talk about all the result findings we got. Yeah.
Does the modality of your data set make a difference here? Like if you here everything looks like images, what happens if you use text or something else?
Yes. So the LabelBench paper, we did it with images, yes. And it is an open source yeah, it's an open source repo, and it has all the necessary parts to incorporate text. We're actually working on that, but for this talk, it will just be images. And
but you don't think there's anything inherently special about it, or like do you think one was better or anything like that?
No, I think usually the way to think about it is actually the task, like what's your y. So when you have x in your input and y, the way we usually think about it is about the y. So we don't talk, like x can be any particular thing. Mm-hmm. So this is mostly classification. Yeah. And so if you do text classification like sentiment analysis or something like that, then everything just works out of the box. If you do something like sequence to sequence, which I will talk in the end, it's a lot different. Yeah.
Yeah, I think if you care about the labeling vision, why don't we just incorporate self-supervised learning, unsupervised learning, and class incremental learning?
Yeah, so those I'm already inherently saying it's in as part of the pre-trained model. So this is mostly for when you adapt your model to a particular domain. So you are doing fine-tuning. So we assume you already have pre-trained using unsupervised learning or self-supervised learning. And like all these techniques, you can use it to build a general pre-trained model. Okay. And then on the particular domain, we can we have just focused on these three methods. But yeah, like you said, you could also do like self-supervised learning on this particular domain. And our code base is actually general enough for that to be incorporated, but for like we can't do infinite amount of experiments. So we just chose like two models that are pre-trained using self-supervised learning. Yeah.
So thinking about fine-tuning the prediction, right?
Yeah.
And like in the active sample selection to get this in-context learning, because fine-tuning is not the only one to training multiple functional tests.
Yes, so it is slightly trickier to say what's in context learning in image.
Okay.
Yeah, so that's a really good question. And also, so like I said earlier, this work has been primarily focused on classification. Usually it's general enough to say for multi-label classification or regression, all these discriminative model, you can, it's usually we are only considering those cases. If in context learning is more like sequence to sequence, it's more like a generative model, which we are exploring now. But for this, I think, we are just considering that. Okay. So we found a lot of new insights in both active learning and semi-supervised learning. So I'm going to talk about the active learning part first. I don't think it's very surprising that when you have active learning and semi-supervised learning and large friction model, it actually gives you the best accuracy gain when you fine-tune a model. So the way to look at these results, again, these plots, x-axis is the number of labels you've collected, y-axis is the accuracy of your model. And so, for example, if you look at random, which is the blue line, versus any of the active learning methods, you actually see that the active learning, adding in the active learning instead of randomly choosing points to label, gives you an accuracy gain. And then if you compare this and that plot, so here you use flex match as your training method, that you just use the traditional supervised training, you also see that the accuracy is higher. And then
What is flex match?
flex match is the semi-supervised learning algorithm.
Yeah.
So comparing these two plots, it says semi-supervised learning is important. Comparing any line with the random says active learning is important. And if you look at ImageNet or experiments on ImageNet, this is our result using CLIP model. That's using ResNet 50, obviously. Of course, CLIP beats everything, or not everything, but obviously it beats ResNet. So it also shows that large friction model is important. So this is, confirms, why you should do all three at the same time, because having one or two of them is not as good as having all three.
Right.
Yeah.
What is identify if it's a bigger ResNet? Like, because it has a lot of parameters. So
Yes. It's small. Yes. So, and also it's not pre-trained. And that's usually what's in the active learning literature, unfortunately. I think there are definitely wide ResNet. So these are vision transformers. CLIP also have wide ResNet, right? So it's not so much about what's the architecture, it's more so about the pre-training.
Yeah, but that's what I'm asking, whether it's about pre-training or whether it's about it's a larger model.
I see. Yeah, so I think it's definitely about both. It's clear that if you just have ResNet, no matter if it's pre-trained or not, it's not going to beat vision transformers that are pre-trained using CLIP. If you have a vision transformer and you train from scratch and you have CLIP pre-trained model, I think CLIP will still be much better. Just because the sample complexity to train a vision transformer, you clearly cannot train a vision transformer to a high accuracy based on 200,000 labels. Yeah.
Oh, never mind.
Okay.
Okay.
Yeah.
When you say that like large pre-trained models gives you the best accuracy gain, I would expect something like if you compared the final accuracies from each of the different like active learning methods, the gap between like the lowest and the highest is like the greatest for large pre-trained models as opposed to something smaller like this.
Oh, yeah. So when I say best accuracy gain, I just mean the best accuracy on each
Oh,
point.
you can get okay.
So like in practice, you just want to get as high accuracy as possible. You don't care about if it's better than random or not. If random gives you the best accuracy, use random. Like there's no reason to use active learning. So I'm here is just a pure statement about, let's say, like if I care about a budget of 300,000, what, like how do I get to this accuracy, right? Or if I care about 400,000, how do I get to that accuracy, right? So I don't care which algorithm I use. I don't care if I'm using semi-supervised learning or which model. I just want to get there, right? So, but it does show like adding all three together does give you the best accuracy. So this is sort of a trivial thing, but it does say, why we are doing this. There are other insights that are more particular to active learning. I know most of the audience here are not active learning, so I will just give you some background. So before LabelBench, for the past 5 years, like I work on active learning, and it's depressing, super depressing, because in 2019, there was this paper called Badge, proposed by a guy called Jordan Ash. He's a researcher at MSR, and he proposed this algorithm, and and then like everyone in active learning is trying to beat this. And particularly he evaluated using supervised training and ResNet 18, I believe. So everyone is trying to beat that algorithm, but if you look at all these papers publishing after Badge, you just see like super tiny gains over Badge. So or even no gains over Badge. So it's not even better than Badge. Badge here is the brownish thing. Here I think Badge you get a slightly better than Badge, but not that much. And another thing is Badge is like, if you look at the gain on CIFAR 10, if you say, well, I just want to reach like 75% accuracy, how many less label do I need? If I run active learning, you see like roughly like 20% label efficiency gain, meaning like to get to the same accuracy, you can save like 20% of the labels. That may be significant if you're labeling like millions of labels, but it's not that impressive, right? And so working on this field is very depressive. So the conclusion before LabelBench was, well, Badge is almost optimal. In fact, Steve, Kevin, and I tried to run subset selection algorithm. So subset selection is if you knew all the labels of a particular data set, how do you choose a subset of it and train on that subset to get to the same accuracy as if you were training on the entire set? And we ran that, and we had a modified version of the state-of-art subset selection algorithm, and it's worse than Badge. Badge doesn't know the ground truth labels. This fixed budget boss, the blue curve, knows about it, and Badge is better. So we were like, yeah, under the setting, Badge is basically optimal. And also, like, it really sucks. Like, it just saves 20% of the label. Why even study it? Well, if you do it on this new benchmark, which is more realistic, which gives you the best accuracy gain, you actually see the value in active learning much clearer. So on CIFAR 10 before, using supervised training and ResNet, you save like 20%. Here we save more than 70% of the labels. So random here, if you see using active learning, you can reach this accuracy over here. Like the best algorithm can reach it over here, which takes like 3,000 labels instead of 10,000 labels. That's a huge win if you were an active learning researcher, because basically for the past 5 years, people are trying to get like 25% instead of 20%, and here is a clear gain over what I've shown you before. So that's the batch result using supervised training and ResNet. This is using semi-supervised learning and using Clip. Yeah.
So it looks like all the active learning methods benefit from this. It's not just like batch.
Yeah. Yeah.
But so there's still no real difference between batch and the other guys when you have all these things mixed in.
I will discuss that as insight number 4.
Okay.
And you actually see batch is not that good.
Okay.
And on C400, this is not something people usually report because they see less than 5% of label efficiency gain. So they save like less than 5%. Well, here, you save 50%. So that just says, oh, maybe active learning is worth studying because now you can actually save a lot of labels. Okay, so all of these results are when you fine-tune your model end to end. And an issue with using adaptive data selection or active learning is, well, if you go back to this framework, there is actually a computation bottleneck. Meaning, initially you would just randomly choose your fixed budget, like say 10,000 images, and then you train your model once. But here, if you're collecting in batches of 1,000, you collect first batch of 1,000, annotate them, collect the next, annotate them. Every time you need to train a neural network. So that neural network training cost is super high, especially if you want to fine-tune a vision transformer. It wasn't that high when you use ResNet, but it is now an issue if you use transformers. And so to give you a more concrete comparison, we roughly see like in model training, we roughly see a 70 times cost, more expensive in neural network training. So because we're using semi-supervised learning, it's usually 7 times of the cost of supervised training. Because we're using vision transformers, that's usually 10x or even 100x, depending on which model you're using. So that's a really high training cost. And if your training cost is so high, then the saving in your annotation cost is not that appealing anymore, right? Because at the end of the day, you want to save the overall the cost, and you don't want to incur $100 more by saving $10. So that's why we sort of explore this selection via proxy idea. And the idea is super simple. So every time, remember, we need to retrain this model again every time we select a batch. Or instead of retraining that entire model, we like freeze the embeddings. We freeze basically n-1 layers or n-2 layers, and only train a linear probe or a shallow MLP on top of those features. And we use that model to still inform our active learning algorithm, say, what's the model uncertainty, what's the what's the representation embedding, or what's the gradient embedding, all of these. So we basically use we only need to retrain this very cheap, very small linear model or shallow network every time we collect a batch. And after this adaptive collection, after getting all my budget exhausted, I will fine-tune the vision transformer end-to-end only once. So that basically aligns with the training cost as the original thing. So if you just use random sampling plus fine-tuning the model end-to-end once, this is roughly a similar cost. And so if you translate that into GPU hours and AWS on-demand dollars, you roughly see that if you use a proxy model, you get like more than 10x in computation cost over if you fine tune the model end to end every time. This is on image. So that's cool, but is this idea actually good for, does that hurt accuracy, right? We're using a much smaller model. We're even if we're using these pre-computed embeddings, it can still hurt our model performance. In fact, we do know that if you train a linear probe, the accuracy is worse than fine-tuning the model end-to-end. So is that sufficient for data selection? And our answer is apparently yes. So especially on the test accuracy. So if you every batch of data collection, if you fine tune the model, you get roughly 0.1%, 0.2% gain over if you were collecting the model using a proxy model like shallow network or linear probe. So that says, so remember, fine-tuning a model will always give you better accuracy, but than using a linear probe. But having a linear probe is actually sufficient enough for quantifying uncertainty or quantifying diversity of your collected data. That's actually sufficient. It's actually good enough for data selection. I think, yeah, so here is just some rough background. If you're just care about accuracy, then if you do zero shot on CFR10, it gives you 91%. If you do linear probing, it gives you 95%. If you fine tune the model, it actually gives you 98%. So fine tuning the model at the end is also very important. But during the data selection, you don't need to fine tune everything. Yeah, so that's the insight number 3. Well, that also concludes like, yeah, using active learning is not going to incur a lot of more computation costs, but it can save a lot of annotation costs. Yeah, the number 4 is what Joe was saying, like, is batch actually better? Have we actually made progress since margin sampling was proposed in like before the 2000s? Not really. That's all that's a bummer for a lot of researchers like Kevin. But then I see like, oh well, yeah, we maybe not, but then we actually are on the right direction now, because really what has been happening is so here, like, margin sampling is the red curve, and it's basically better or on par with the pink curve, which is batch. And basically what that suggests is that we are really overfitting to the benchmarks that we have been evaluating against. Yeah, so yeah, that opens up a lot of future.
Sorry, badge is the purple one?
Badge is the pink one.
Oh, okay.
Yeah. So it's over there. It's not like, yeah, it's not core set. Core set is done. Yeah. Yeah. So the 3 takeaways for active learning researchers are: badge is only almost optimal on this benchmark we have been evaluating against using supervised training and ResNet. And people probably should spend their smart time on something else like LabelBench, not that benchmark. And then, okay, we also show that active learning is great now. It's not useless. And really over the past 5 years or more, we have been overfitting to the benchmarks. Okay, cool. The semi-supervised learning insights are shorter. So insight number 1 is the same insight, but here we vary different semi-supervised learning algorithm. And I think basically so this is using an algorithm called pseudo label. This is called UDA, which is, and then the flex matches, which we have shown before. And if you look at these, and I don't think I had the plots of the passive training here, but imagine there's a passive training plot. All these are better than that. So it just confirms us the story that, yeah, adding semi-supervised learning, even if you're not using flex match, the state of art, you're still getting a lot of accuracy gain. This is on C400, basically the similar story. The next one is if you vary which semi-supervised learning algorithm you use, the relative performance of them stays very similar when you choose different active learning algorithm. So what that means is, if you look at, say, the margin sampling curve here, the margin sampling curve here, margin sampling curve here, you see that pseudo label performs worse than UDA, than flex match. If you use a different one, say Corset, you also see that pseudo label is worse than UDA, than flex match. So for any active learning algorithm, if you compare the three semi-supervised learning algorithm, they roughly stay in the same order. So that also suggests like you can probably study semi-supervised learning under this framework while fixing which active learning algorithm you use. The other way is the same. It also applies. The relative performance of active learning algorithms stays very similar when you choose different semi-supervised methods. So look at this plot. These algorithms roughly perform the same, and then there's Corset. Very loosely speaking, random and their order is roughly similar to the order of these methods, and then Corset, and then random, and same applies to the last plot. And really, like, 0.1% difference here is not that significant. So you can actually, this basically suggests that you can study active learning while fixing one of the semi-supervised learning algorithm. Preferably flex match, because that's the one giving you the best accuracy. Obviously, this doesn't discourage you from proposing a combination of semi-supervised learning algorithm, active learning algorithm, but that hasn't been something people have done before. That's also a possible direction to go in. Yeah, so those are the insights. Very quickly, I will just go through what we have been thinking about in further developing LabelBench, and also the sequence-to-sequence models that several of you have been hinting at. So LabelBench, well, it can be used for more than active learning semi-supervised learning. I have hinted at this before, but like you can also use it for data subset selection. So if your goal is not to train a model by annotating efficient data points, but your goal is to know, by knowing which data you have, and choose a subset of them, there's no reason why you can't use a pre-trained clip model in the process. There's no reason you can't use a semi-supervised learning once you've chosen the subset. So this is something that we have been actively discussing internally. And if any of you is working on this field or is interested, definitely get in touch. I know Steve Musma is really interested in this, and he has been saying he wants to work on that, but he hasn't made any effort yet. Oh, this is recorded. Shit. Maybe he has. I just don't know. My bad. And then there's another thing. It's traditionally called experimental design. You can also think of it as a one batch active learning thing. So experimental design was mostly started from stats, and it's usually studying linear models. More modern term is one batch active learning. basically, instead of adaptively choose which data point to get labels on, you just have one chance. You just say, well, I have a budget of 10,000. Which of the 10,000 should I get data to annotate on? And apparently there are strategies that are better than randomly choosing them. So yeah, we can also apply LabelBench to that field. Again, you can use semi-supervised learning to train the model. You can also use clip model, pre-trained clip model to get higher accuracy. Like there's no reason not to do that. So we also we basically make data subset selection and experimental design much easier to work with in LabelBench in these more modern scenarios. The third thing is more engineering focused. We want to sort of integrate these commercialized annotation platforms into LabelBench so that if you have a new job of annotating something, you can just come to LabelBench, use whatever code we have already, or plug in your trainer or plug in your model, and then start getting annotations from I don't know, Scale or Labelbox, these services. Yeah, so if you are interested in any of these, definitely get in touch with me. And then the second thing we have been working on is less about semi-supervised learning, more just geared toward active learning, is because sequence-to-sequence models have really just recently gotten popular. So or generative modeling in general. So we are thinking about there's a lot of human annotation involved in this. So when you do supervised fine-tuning, you need to generate human label response to these particular prompts. When you do ROHF, you have a lot of people just going in and ranking which one is better. So basically what we have been doing is creating a new benchmark, and it's a good lesson to learn from the previous benchmark is we should really have a benchmark just in the beginning and update this benchmark as we move along instead of fixing it on just very outdated ResNet training. So this is something that we are developing right now. I can give you some idea on what's happening, like so like the open questions that our active learning can solve are, like, for example, in supervised fine-tuning, like you have a bunch of prompts and probably more prompts than you can get human response on. So which prompt do you choose to get human response on? So that is supervised fine-tuning. For preference-based training, so for each prompt you have multiple candidate response, and you say, well, and then you ask people to come in and rank them. So first of all, which prompt do you get people to rank? Which response do you get people to rank on? And there's a third thing that I don't remember what I wrote. But so yeah, these are all open problems. And the biggest challenge in here is still the computation cost. And after working on these problems, I could say, like, what we have done in LabelBench using the proxy model is unlikely to work, because there's no way you could just embed everything into a high-dimensional space and train a linear classifier, because everything is decoder now. So it's conditioned on previous generated text, and it's not clear how we can build a proxy model for that. So yeah, so these are all open questions, and we're still exploring what's the most valid way of applying active learning in these scenarios while not incurring a huge amount of computation cost. All right, if you have some ideas, let me know. We can collaborate. You can be one of those people shown on the slides. Okay, yeah, that's it.
referred, the LabelBench work. Have you also tried other vision foundation models or created the own?
Yeah, we also tried Coca. I don't have those results here. So we can just, yeah. So there's Flip and there's Coca. They yield basically similar results. So they yield similarly, like you see this a lot of accuracy, label efficiency gain. You see relatively the active learning algorithm performs similarly when you rank them. And so, yeah, we have those in the paper, but I don't have it there.
I have a question. So I observed that recent semi-supervised method, they use one sort of inputs to train, which means that on several times, for a fully trained model, you can spend an hour to train, and for semi-supervised learning model, you need 3 days. So I think it's not realistic at all, and I wonder how do you comment on this kind of approach compared with another approach, which is to sample or let's say retrieval in the related data from a large database, right? Now we have that data set, and then train the model on such retrieval.
I see. Well, so I think the second, so okay. So let me just confirm the question here. So you're saying some semi-supervised learning algorithm these days takes 1,000 more times to train, and then why don't we take some retrieval like k-nearest neighbor of a data point, assign them a particular label, and train on those. I mean, the second one is also a semi-supervised learning algorithm. If you think about it, like it is sort of assigning pseudo labels, but using a different strategy. And then I would say, like, yeah, the first one, I think if you have a semi-supervised learning algorithm takes that much more compute, you really need to question the usefulness of your algorithm, right? Like clearly here, flex match is only taking 7 times more compute, not 1,000 times more. If there's an algorithm that performs super well and takes 1,000 times compute, maybe that's worth it. It's always case by case, depending on your application. Maybe like 1% accuracy gain means $10 billion, or it maybe means $100. So it's always the decision in real life. Yeah.
I think currently people do not assign pseudo labels for retrieval. For example, people just right, you use KN to, for example, for images, they can use KN to sample images from a large database like Leading. And then they can directly get the label from the database.
I see.
There is no there is no pseudo label.
Yeah, so basically what you're saying is usually in semi-supervised learning literature, you may do retrieval, but it's in the retrieval of ImageNet. Like it's in the same data set. But you can actually take advantage of external data set like Lion, or some of those data sets. Totally, yeah. I don't see why not to do that. Yeah. If it performs better than FlexMatch, or maybe even it makes sense for you to do that with FlexMatch, right? Like FlexMatch is an algorithm. It doesn't necessarily need to be one way or another, right? You can always say my unlabeled data is from a much larger pool than what I have. Yeah.
Have you thought about like auto labeling methods?
To be honest, so my understanding towards auto labeling is pretty naive. So maybe you can give me some background information on that. Like what's the goal there?
It's just like instead of having a human annotator, you have like a robot, which like it's like like maps out regions, that it like where it thinks there's like high confidence of like it having the correct label.
Uh-huh.
So it, you know, it basically reduces like the cost of food management.
Yeah, so I don't know why that's how, maybe it's different, but I don't know how that's different from using active learning and semi-supervised.
Well, active learning is just like a process of picking labels you want.
Yeah, and then semi-supervised learning can automatically tell you
I see.
what are other things you should label. So yes, and also another evaluation metric that I didn't mention is pool accuracy. This is something people look at in active learning is, suppose I have this large unlabeled data set, I have labeled part of it, but how do I do overall on this pool? So I would use my current best model to predict on the pool, on the unlabeled data in the pool, and look at the accuracy on the whole thing. So that's, I believe, something people in auto labeling care about. That's a metric or objective that people care about. Yeah, I am not exactly sure how to distinguish those with something like active learning plus semi-supervised.
Okay.
Yeah. Thank you.刚才在 record 的时候，